Welcome to Physics Rescue. This topic is the turning effects of forces. We'll start with the definition of the moment of a force. The moment of a force or torque about a pivot is the product of the force and the perpendicular distance from the line of action of the force to the pivot. All right, so it's represented by m is equal to F times d, m being the moment, F force applied, and d is the perpendicular distance. Some books would write m is equal to F d perpendicular to differentiate from work done, which is also force times distance, but distance moved in the direction of the force. For some books, work done will be represented by Fs, right? S being the distance, okay, to differentiate them. Right, so what is the meaning of the line of action of the force? Okay, we will talk about this 2 slides later. First of all, moment is a vector quantity, all right, which means that it involves both magnitude and direction. The direction of the moment of a force can be clockwise or anti-clockwise, right? So in this case, the pivot, okay, we first of all look for the pivot, or you need to determine what the pivot is. This one will be the pivot, and just like a clock, the middle of a clock, this force F will cause this bar to turn clockwise, all right? So the direction of movement will be clockwise. And for the second one, right, the pivot being at the same place, the force will cause the bar to turn anti-clockwise. Okay, so moment is a vector. Vector meaning that it must have direction. Okay. We are looking at some examples now to illustrate the meaning of line of action of the force. So we have a wrench here with a 5 Newton force making it turn in an anti-clockwise direction. So to find the moment, it is pretty straightforward here. It is just force times perpendicular distance. And since the force is at right angles to the perpendicular distance of 0.2 meters, it is pretty straightforward. All right, so it's just 5 times 0.2. If we are using two significant figures, then it will be 1.0 Newton meters anti-clockwise. I'm going to write in short form because this is a vector, moment is a vector, so we always need to write the direction. The second example here, the 5 Newton force is no longer at right angles to the 0.2 meters. So if we want to find the turning moment over here, we will need to know what this distance is, all right, which is, if I extend this 5 Newton force, right, and it makes a right angle with this, okay, this distance is actually what we will need, right? This is the perpendicular distance. Okay, so when we say the line of action of the force and the perpendicular distance, this is what we mean. So let's say, for example, that this distance is 0.10 meters, all right? So then our moment will be 5 times 0.1, which is 0.5 Newton meters anti-clockwise. So what I'm trying to show here is that when we talk about the line of action of the force, you will need to multiply it by the distance that is perpendicular to that line of action of the force from the pivot. Right, so let's take a look at the third example here. And again, this wrench is in a different position. So if we extend that 5 Newton force here, what we want is to have that perpendicular distance to the pivot. So knowing that the pivot is the center of the nut, all right, the perpendicular distance that we want would be this, right? So what this distance will be okay, for this example, I'm just going to take it as, say, 0.12 meters, all right? So in this case, then, your moment will be, the principle of moments, it states that for a body in equilibrium, the sum of anti-clockwise or clockwise moments about a pivot is equal to the sum of anti-clockwise moments about the same pivot. All right, the keywords for the principle of moments must be there, and very importantly, that object must be in equilibrium for the total resultant moments to be zero. Right? In other words, the total clockwise moments and the total anti-clockwise moments is equal. And we can look at the definition of equilibrium, right? Or the two conditions for equilibrium. For a body to be in equilibrium, two of these conditions must be met. One is the resultant force must be zero, and secondly, the resultant moments must be zero. All right, so when we talk about resultant force being zero, it can be that the upward force is equal to the downward force. So if you have the weight, say for example, is 40 newtons, the upward force must be 40 newtons. And in the case of moments, very commonly you have say a seesaw, all right? So let's say this seesaw is being supported at the CG at a point of the center of gravity by a pivot, right? The weight, so let's say the weight is 40 newtons, and there being no other forces, only the upward force of the pivot on the plank, right, on the seesaw plank, then the upward force will be also 40 newtons if this seesaw is at equilibrium. Right, so this is often forgotten as compared to the principle of moments, right? This principle of moments is what students will remember most of the time. They will remember anti-clockwise moments, right? Or ACWM is equal to total clockwise moments, or CWM. They will remember this, but they will tend to forget that the resultant force will also have to be zero. And we need both, right, to solve some problems. Okay, and let's look at some examples here. Okay, this diagram shows that there's a light seesaw. What do we mean by a light seesaw? The word light means that we can ignore the weight of the seesaw, right? Ignore the weight of the seesaw. Okay, otherwise you would have to know where the CG is, and you need to consider the force or the weight acting downwards because of the weight of the seesaw, right? So the boy weighs 300 newtons, so let's draw the force from the boy. 300 newtons. Okay, 300 newtons. And the father's weight, right? We do not know, so let's call it WF for weight of the father. And then we have, we want to find out what the weight of the father is. That's very straightforward. We just apply the principle of moments. So you can write by the principle of moments, the total anti-clockwise moment is equal to the total anti-clockwise moment is equal to the total clockwise moment. So in this case, it's just 300 times 1.5, right? The force, the weight of the boy multiplied by his perpendicular distance to the pivot, and then the weight of the father multiplied by the perpendicular distance to the pivot, right? So if you work it out, 300 times 1.5 is 450, then times 2 you get 900 newtons. Now number two you would need to you will need to apply that second condition for equilibrium, and that is the total resultant force is 0, right? So when the resultant force is 0, that means that the upward force will be equal to the downward force. Right? So when the upward force is equal to the downward force, we already know that the downward forces are, okay, the weight of the boy, 300 newtons, and the weight of the father, which we have found to be 900 newtons. Now the upward force would have to be that upward force acting by the pivot on the seesaw, on the plank. So let's call this upward force Fp for pivot, right? So Fp will be equal to, Fp is the only upward force here. It will be equal to the weight of the boy plus the weight of the father. So it will be 1,200 newtons. All right, so that will be the upward force. So this example shows that you need to have the both conditions of equilibrium, right, to be able to solve the question. One being resultant moment is 0, and secondly, resultant force is 0. Now, solving moments questions, we should have certain procedure, right, to go about solving the problems, especially if the problem is complex, right? So these are steps to help you to consider when you encounter a problem. What are the things to consider in a sequential manner? So first thing, we need to identify where the pivot is. All right, it is not always obvious, right? Although most of the time it will be obvious because it will be a joint or a hinge or a triangular object that denotes the pivot, but it is not always the case. So it's important to identify where the pivot is, and number two, draw the forces acting on the object. So as you remember from the previous question, right, the upward force of the pivot on the plank or on the seesaw plank is not drawn beforehand, and you need to be able to draw it in, all right, to recognize that there's a force there, right? So you need to draw the forces, and we need to include the weight of the object, all right, unless the question says that it is light or you can ignore the weight of the object. And then we have to identify the perpendicular distances of the force to the pivot, right? Remember that it has to be the perpendicular distance, all right, from the line of action of the force to the pivot. And fourthly, we solve either using principle of moments, or if for a case where the object is turning, right? Let me give an example here. So let's say we have an L-shaped metal piece, okay? And it is pivoted at the corner of this L-shaped metal piece, all right? So let's say the pivot is here. So this L-shaped piece is able to turn either clockwise or anti-clockwise. And let's say there is a force acting over here. Let's just take, say, for example, 400 newtons. All right, and let's say that the distance over here is, let's take 0.5 meters, for example, 0.5 meters. Okay, let's draw this a little bit longer. So let's say that this metal piece, right, is longer over here, and let's say we want to find what is the force that's acting over here at, say, 1 meters away from the pivot. All right. So in this case, the 400 Newton force is causing this metal piece to turn clockwise, and as a result, there will be a clockwise moment. And if we want to find F, we cannot write anti-clockwise moment equal to clockwise moment, because both F and the 400 Newton force will cause a clockwise turning moment. So in this case, our working would be to write M1 equal to M2, right? The force clockwise moment caused by the 400 Newton force is equal to the clockwise moment, okay, caused by F, which is or the clockwise moment that's as a result of that 400 Newton force exerted at 0.5 meters, right? So in this case, obviously the answer would be 200 newtons. Yeah, all right. So this, we are finding the force, so there's no need to write the clockwise or anti-clockwise. So in this case, this illustrates the point that we cannot always use principle of moments. All right. Sometimes we need to write the moment, clockwise moment equal to clockwise moment, or anti-clockwise moment equal to anti-clockwise moment, depending on the question. All right. So if it's turning in one direction, then the anti-clockwise moment equal clockwise moment will not apply. All right. Okay, let's look at this example here. Okay, using the steps that we have learned earlier, right? Let's look at the question. It says that a uniform meter rule is pivoted. Now, when you look at the word uniform, what does it mean to you? All right, uniform means that the weight of the object acts from the center of the object. Okay, so the CG of this object is at the center. And in this case, since it's a meter rule, then the CG would naturally be at 50 cm, right? At the midpoint of the meter rule. And it's already pointed out over here. It's already labeled. So what we need to do, draw the forces, the weight of the meter rule, right, which is unknown. So let's call this the weight of the meter rule. Okay, I'll just call it W. Okay, let's continue reading the question. When loads of 2.4 newtons and 0.60 newtons are hung at different positions, the ruler balances horizontally. Now, take note that when they give you a value 0.60, it is telling you that two significant figures is being used, right? So we need to be watchful about that. So using principle of moments, all right, total anti-clockwise moment equal to total clockwise moments. So we have all the forces. Do we have any other force here? There is an upward force of the pivot acting on the plank, but since we are not finding that for this particular question, you don't really need to draw that. Okay, so there are no other forces here. There are just 1, 2, and 3 forces here. All right, and 2 of them are acting to create a clockwise turning moment, and 1 is causing an anti-clockwise turning moment. Right, so 2.4 newtons is causing that anti-clockwise turning moment. Do we need to convert the cm to meters? In this case, because cm is used on both sides, you do not need to convert because they will cancel off anyway. So you just need to be watchful about the perpendicular distances. Because for W, it's quite straightforward, W times 30, right? But for 0.6 Newton, you need to be careful, and you must remember that the distance, the perpendicular distance, is from the force to the pivot, right? And so some students will forget and they take this 15 cm. But this 15 cm is not the perpendicular distance from the load to the pivot. It is only up to the CG, which is not what we want. So it is actually 15 plus 30, right? So it's 45 cm. Okay, so as long as all the lengths in your working are the same unit in cm, you do not need to convert to meters. All right, so carrying on with this, we have the 36 over here is equal to 30W plus 0.6 times 45 is 27. So 30W is equal to 36 minus 27, so which is 9. So W will be equal to 9 divided by 30, so you get 0.30 newtons.